Hey there, chemists. In the last lesson, we looked at addition reactions to alkenes and a little bit to alkynes. We're going to look at some more addition reactions today, specifically with the theme of hydration, meaning adding water. And there's a couple of different ways to do that, and it makes a very useful functional group, the alcohol. So we're devoting a whole lesson just to this, the addition of H and OH across what used to be a pi bond. So let's look at the ways that we can do that just with alkenes. The simplest one, which I'm just going to call hydration with acid, and I'm using the same methyl cyclopentene that we used in our previous lesson, again, just as an example of an alkene, but you can imagine virtually any simple alkene undergoing these types of reactions. If you treat an alkene like this, you actually get the opposite of what you get for a dehydration. You get the alcohol. In this case, you get the more substituted tertiary alcohol. So, some key features of this undergoes Markovnikov addition, meaning the H goes to the less substituted carbon and the OH goes to more. And we're going to draw the mechanism of this, and you'll see exactly why. So, let's redraw methyl cyclopentene. Now this is under acidic conditions, so the first step is something gets protonated. A proton is an electrophile, things attack protons. The only thing that we have that's nucleophilic is this pi bond. So draw an arrow from the pi bond to the H. That will break the pi bond. You'll get an H on one of the carbons and a plus on the other, and you end up getting the more substituted cation, the tertiary one in this case. That's Markovnikov's rule. From here, we have water. Water can now act as a nucleophile. When water sees this plus charge, the nucleophilic electron pairs on the oxygen form a bond. So draw an arrow from the oxygen to the plus charge. So you have a new carbon-oxygen bond, and the two hydrogens that were on the water are along for the ride. And now the plus charge is on the oxygen instead of the carbon. So how do we finish up? We need to lose one of those H's. You could use another water molecule if this is your solvent. You could use another starting alkene. Virtually anything can act as a weak base to take away one of those extra H's. The OH bond breaks, and you get your neutral alcohol. And you should notice a couple of things. Number one, we regenerate H+, don't we? We actually just made H3O+, and that's actually what this reaction uses. So they can say this is a catalytic reaction because we consumed an H+, and we regenerated it in the end. That's what it means to be catalytic. And what's more is this is actually a very reversible reaction. So you don't have to do this, but you can go and put reversible arrows in every part of your mechanism, and that should be reminiscent of the opposite process, taking an alcohol, doing a dehydration to make an alkene. The difference is you have a net production of water in that direction. Here we have a net consumption of water, and that's how you control this in the laboratory. You either exploit Le Chatelier's principle by adding water or taking water away and shifting the equilibrium in one direction or another. So this goes with Markovnikov addition, but is there a way we could get it to be non-Markovnikov, and is there anything that's more stereoselective about this? And that's what the remaining two reactions will answer. So the next reaction, which is called an oxymercuration reduction, oxymercuration/reduction, is a different way to do the exact same transformation that we just saw. If I start with methyl cyclopentene and I treat it with a source of mercury 2, those are just acetate anions, in the presence of water followed by sodium borohydride, which is a reducing agent, you get, in this case, a tertiary alcohol. So what's the point if I have this other variation of this reaction? Well, this is a much milder reaction, and it's stereoselective. It is Markovnikov, so we get that regiochemical aspect of it, but it also occurs with anti-addition. Now I can't tell in this example, but you'll see in the mechanism why the new OH and the new H are actually added to opposite faces of this ring. Again, I can't tell in this example, but if we had an example that was differently substituted in the beginning, you would be able to see it. So let's show how this occurs. Let's redraw methylcyclopentene. And what we have here is a source of mercury 2, Hg2+. That's what mercuric acetate is. It's an electrophilic source of mercury. So start off by drawing an arrow from the pi bond to the mercury. And you actually make a mercurium ion intermediate. Remember that bromonium ion from the previous lesson? The same type of thing forms here. This actually becomes still a 2+ on the mercury. It would have been +1 on the mercury and then a +1 on the carbon, but as soon as it cyclizes, which many people argue it happens all in the same step here, you get this. It's likely that you form this directly. Anyway, it's that 3-membered ring, this mercurium ion, which does the same thing that the bromonium ion does. It blocks one face of the ring. Now, we'll get a racemic mixture of this intermediate, but when my water sees this, it will do what we saw in halohydrogen formation and bromination in the previous lesson. It will attack the more substituted carbon, and in this case, that's the tertiary one, and it will attack it from the opposite face of wherever that mercury is. So this is what I mean by saying this occurs with anti-addition. So my new water molecule is coming out of the page in this example. It now has a plus charge on it. Whereas my mercury, it's still attached to the other carbon, and as a result it has a +1 charge on it. Now this will lose an extra H. Water can take away that extra H, and you get an alcohol on one carbon. And we still have this mercury attached to the other. And this actually is the oxymercuration product, and that's why they call this oxymercuration, because you're adding an oxygen and a mercury across what used to be a pi bond. This finishes up with a reagent called sodium borohydride, and I'm going to say skip mechanism for now. Skip mech, because it's a little more involved than what we need to go into in this level of the class. I will tell you, it reduces the carbon-mercury bond down to a carbon-hydrogen bond. And that's all you need to know at this stage of the course. But there's the anti-addition of the OH and the H. I can't tell because I didn't actually create an asymmetric carbon in this, but if it was a different alkene, it would. Okay, so that's how we get a more stereoselective version of this reaction. Is there a way I can get a non-Markovnikov? Yes, that's the last one for alkene hydration. It's called hydroboration / oxidation. And hydroboration, if I start with methylcyclopentene, gives me the other constitutional isomer, where instead of having an OH on the more substituted carbon, it ends up on the less substituted carbon. We get the non-Markovnikov. And what's more, the OH that I add is actually syn to the H. So this is the opposite of the one right above it in every respect. This is non-Markovnikov. And this undergoes syn addition. So even if you don't remember the mechanistic details of each of these, if you remember the consequences of one, just know that the other is the opposite. But as with all of these, let's explain why we get syn addition and why we get non-Markovnikov. So let's redraw methylcyclopentene. And I'm going to draw out the borane molecule. Borane, BH3, looks like this. Remember, boron has only a valence of 3. It's a very electrophilic boron, but there's no formal charge. And in one step, the pi bond attacks the electrophilic boron, and the boron hydride bond breaks and sends those electrons with the hydrogen to the more substituted carbon. And there are other borohydride reagents where sometimes this is actually R groups instead, and those work even better because they prevent over-addition if that's an option, and they sterically keep this boron out of the way of the more substituted spot. This is why you get the H on the less substituted carbon. So the H goes, on the more substituted carbon. The H goes on the more substituted carbon. The boron goes on the less. Now this is the part that gives you a syn addition right here. And that's it for hydroboration. That's step one. It turns out the other boron hydrogen bonds can actually attach to other alkenes, and you can get very large molecules where 3 equivalents of the starting alkene can actually react with the 1 borohydride in the beginning, but they all undergo the following after that. So I'm just going to show what happens after that. After that, we treat this with oxidizing conditions, specifically basic peroxide. Basic peroxide looks like OOH minus, that's the peroxy anion, and that will form a bond with the boron. Everything else is along for the ride. So now I have a new boron oxygen bond and an OH, and as a result I have a negative now on the boron. So I get a borate intermediate. And then this rearranges so that the carbon-boron bond breaks and it forms a carbon-oxygen bond right there. And we can draw that with an arrow that looks like that, from the carbon-boron bond to the oxygen, and the OH leaves. Under basic conditions, you can get that to happen. This is very basic. So now we have an oxygen attached to a boron with other H's. Oops, there we go. And now we're swimming in hydroxide. And I'm not going to show all the rest of this, but I'll show a little bit of it. That hydroxide actually picks up the borane, kicks out the oxygen. So you get alkoxide that looks like that, and this is what picks up an H from water or any proton source, and that's how you actually get your alcohol. All you really need to know is that you get syn addition and you get a non-Markovnikov isomer in the end. Okay, so by the way, I arbitrarily chose those H and OH bonds to be drawn into your screen. They can certainly come out of the screen. You will also get the racemic mixture, the enantiomer of this, but they will both be syn. So let's do one practice example that just applies one of these reactions to slightly different conditions. This is called an alkoxymercuration. And it says this can be used with an alcohol as a solvent instead of water. And instead of adding H and OH, we add H and OR. So this is exactly like the reaction we have up here, but instead of water, they're giving us an alcohol as a solvent. And let's see if we can figure out what happens by drawing a little bit of the mechanism. So if I redraw methylcyclopentene, mercuric acetate is just the mercury 2 ion. The pi bond attacks the mercury. We get our mercurium. So far, nothing different. Now at this point, if I look at what I did up above, water attacked the more substituted carbon. I don't have water, I have ethanol. Okay, ethanol is just organic chemistry's version of water. So draw an arrow from the oxygen and ethanol to the more substituted carbon. That's the one that feels like it's positively charged. That breaks the carbon-mercury bond. And you get a new carbon-oxygen bond. But that ethyl is along for the ride. And we still have our mercury. And if I look up above, we can actually now mimic the same subsequent steps. So I'm just going to say same as before. We'll lose that extra H. Sodium borohydride will reduce the mercury down to a hydrogen. and you'll get an ether in the end. So in addition to the Williamson ether synthesis, we now have a second way to make an ether. It's using oxymercuration, but with an alcohol instead of water. Okay, so those are 3 reactions that you can use to take alkenes and turn them into alcohols, Markovnikov or non.